Welcome to the first section of the course, Dimensionality Reduction. In this section, we'll implement dimensionality reduction techniques such as PCA, singular value decomposition, SVD, and iterative feature selection method using a practical dataset and R programming language. Why dimensionality reduction is a business problem and what impact it may have on the predictive models. An R programming-based implementation and interpretation of results in a practical project. Now let's move on to the first video. Why dimensionality reduction? In this video we'll learn about techniques available for dimensionality reduction, which technique to apply where and principal component analysis. In data mining, traditionally people used to apply principal component analysis, PCA, as a method to reduce the dimensionality in data. Though now in the age of big data, PCA is still valid. However, along with that, many other techniques are being used to reduce dimensions. With the growth of data in volumes and variety, the dimension of data has been continuously on the rise. Dimensionality reduction techniques have many applications in different industries, such as image processing, speech recognition, recommendation engines, text processing, and so on. The main problem in these application areas is not only high-dimensional data, but also high sparsity. Sparsity means that many columns in the dataset will have missing or blank values. In various statistical analysis models, especially showing a cause and impact relationship between dependent variable and a set of independent variables, if the number of independent variables increases beyond a manageable stage, for example 100 plus, then it's quite difficult to interpret each and every variable. For example, in weather forecasts, nowadays low-cost sensors are being deployed at various places, and those sensors provide signals and data that are being stored in the database. When 1,000 plus sensors provide data, it's important to understand the pattern, or at least which all sensors are meaningful in performing the desired task. Another example from a business standpoint is that if more than 30 features are impacting a dependent variable, for example sales, as a business owner I cannot regulate all 30 factors and cannot form strategies for 30 dimensions. Of course, as a business owner, I'd be interested in looking at 3 to 4 dimensions that should explain 80% of the dependent variable in the data. From the preceding 2 examples, it's pretty clear that dimensionality is still a valid business problem. Apart from business and volume, there are other reasons such as computational cost, storage cost of data, and more if a set of dimensions are not all meaningful for the target variable or target function. Why would I store it in my database? Dimensionality reduction is useful in big data mining applications in performing both supervised learning and unsupervised learning-based tasks to identify the pattern, how the variables work together, display the relationship in a low-dimensional space, compress the data for further analysis so that redundant features can be removed, avoid overfitting as reduced feature set with reduced degrees of freedom does that. Running algorithms on a reduced feature set will be much faster than the base features. 2 important aspects of data dimensionality are, first, variables that are highly correlated indicate high redundancy in the data, and the second, most important, dimensions always have high variance. While working on dimension reduction, it's important to take notes of these aspects and make necessary amendments to the process. Hence, it's important to reduce the dimensions. Also, it's not a good idea to focus on many variables to control or regulate the target variable in a predictive model. In a multivariate study, the correlation between various independent variables affect the empirical likelihood function, and affects the eigenvalues and eigenvectors through Covariance Matrix. Now we'll look at the techniques available for dimensionality reduction. The dimensionality reduction techniques can be classified into 2 major groups: parametric or model-based feature reduction, and non-parametric feature reduction. In non-parametric feature reduction technique, the data dimension is reduced first, and then the resulting data can be used to create any classification or predictive model, supervised or unsupervised. However, the parametric-based method emphasizes on monitoring the overall performance of a model and its accuracy by changing the features and hence deciding how many features are needed to represent the model. The techniques generally used in data mining literature to reduce the data dimensions are non-parametric, PCA method, parametric method, forward feature selection, backward feature selection. We're going to discuss these methods in detail with the help of a dataset using R programming language. Apart from these techniques mentioned earlier, there are a few more methods, but not that popular, such as removing variables with low variance, as they don't add much information to the target variable, and also removing variables with many missing values. The latter comes under the missing value treatment method, but can still be used to reduce the features in a high-dimensional dataset. There are 2 methods in R, PRComp and PrinComp. but they use two slightly different methods. PrintComp uses eigenvectors and PRComp uses SVD method. Some researchers favour the PRComp as a method over PrintComp method. We're going to use two different methods here. So, how will we know where to apply a particular technique? The usage of the technique actually depends on the researcher, what he is looking for from the data. If you're looking at hidden features and want to represent the data in a low-dimensional space, PCA is the method one should choose. If you're looking at building a good classification or a prediction model, then it's not a good idea to perform PCA first. You should ideally include all the features and remove the redundant ones by any parametric method, such as forward or backward. Selection of techniques vary based on data availability, the problem statement, and the tasks that someone is planning to perform. Let's take a look at principal component analysis. PCA is a multivariate statistical data analysis technique applicable for datasets with numeric variables only, which computes linear components of the original variables, and those principal components are orthogonal to each other in the feature space. PCA is a method that uses eigenvalues and eigenvectors to compute the principal components, which is a linear combination of original variables. PCA can be used in regression modelling in order to remove the problem of multicollinearity in the dataset, and can also be used in clustering exercise in order to understand unique group behaviours or segments existing in a dataset. PCA assumes that the variables are linearly associated to form principal components, and variables with high variance do not necessarily represent the best feature. The principal component analysis is based on a few theorems. The inverse of an orthogonal matrix is its transpose. The original matrix times the transposed version of the original matrix are both symmetric. A matrix is symmetric if it's an orthogonally diagonalizable matrix. It uses variance matrix, not the correlation matrix, to compute components. The steps to perform principal component analysis are: get a numerical dataset. If you have any categorical variable, remove it from the dataset so that mathematical computation can happen on the remaining variables. In order to make the PCA work properly, data normalization should be done. This is done by reducing the mean of the column from each of the variables for all the variables. Ensure that the mean of the variables of the transposed data should be equal to 0. We applied the normalization formula. Calculate the covariance matrix on the reduced dataset. Covariance is a measure of two variables. A covariance matrix is a display of all the possible covariance values between all the different dimensions. The sign of covariance is more important than its value. A positive covariance value indicates that both dimensions increase together and vice versa. Similarly, a negative value of covariance indicates that with an increase in one dimension, the other dimension decreases. If the covariance value is 0, it shows that the two dimensions are independent of each other and there is no relationship. Second, calculate the eigenvectors and eigenvalues from the covariance matrix. All eigenvectors always come from a square matrix, but all square matrices do not always generate an eigenvector. All eigenvectors of a matrix are orthogonal to each other. Then we have to create a feature vector by taking eigenvalues in order from the largest to smallest. The eigenvector with the highest eigenvalue is the principal component of the dataset. From the covariance matrix, the eigenvectors are identified and the eigenvalues are ordered from the largest to the smallest. Feature vector is a set of all eigenvalues, eigen1, eigen2, etc., until eigen14. Lastly, create low-dimension data using the transposed version of the feature vector and transposed version of the normalized data. In order to get the transposed dataset, we're going to multiply the transposed feature vector and transposed normalized data. Let's apply these steps in the following section. So, we learnt about dimensionality reduction in this video. That will arm us for further sections.